So our last talk is a virtual talk. It's by Yuanji Li, who's an assistant professor from Tsinghua University. He's working on satellite networks, mobile networks, and their security. Could you please play the video?
Hello everyone, I'm Yuanji Li from Tsinghua University. In this talk, I'm going to show you whether it is worth pushing 5G and beyond to outer space, and how to achieve so with the stateless mobile core network design. This is a joint work with He Wu, Wei, Lixin, Yimei, Jianping, Qian, Jun, and Ziqi. Mobile networks, such as 4G, 5G, and beyond, have successfully served billions of users. However, terrestrial mobile networks face several fundamental limitations. They have not been able to cover rural areas, developing countries, aircraft, or oceans with 3.7 billion unconnected global users. Achieving so requires tens to hundreds billions of dollars of infrastructure deployments, which is simply not affordable by mobile operators. Moreover, their terrestrial infrastructure is also vulnerable to disasters such as earthquakes or wars. To solve these problems, pushing mobile networks to space seems a promising solution. Mobile satellite communications have been operational for decades since the 2G era. They complement terrestrial networks coverage to remote areas at lower costs. The recent low Earth orbit or LEO satellite constellations, such as Starlink and OneWeb, further promise competitive bandwidth and latency to terrestrial networks. To this end, the industry is actively extending 5G and beyond to LEO constellations with standardizations and early adoptions. Pushing mobile network functions to space also boosts new value propositions. It could allow our commodity phones to directly access satellite services using 5G. This has been made possible by recent startups like ASD Space Mobile and Link. Apple and SpaceX are also thinking about enabling satellite services in our smartphones. Moreover, it could also enable internet access to trillions of IoT devices in remote areas without terrestrial network infrastructure. Even more, satellites let local operators expand their business to international services without relying on competitive operators' roaming infrastructure. This yields more revenues for the operators. Let's look at how mobile satellites work in space. The classical geostationary communication satellites are mostly standalone mirrors. They just reflect signals between terrestrial terminals and the ground station within the satellite's coverage. This mode is expensive for the recent low Earth orbit satellites. Each LEO satellite at lower altitudes has very low coverage, so most nodes in remote areas without ground stations cannot be served. Instead, the telecom industry has started to experiment with LEO satellites with higher layer 5G functions. ASD Space Mobile and Link have launched LEO satellites as a 5G radio access functions. On December 2021, China Mobile and Huawei also launched a LEO satellite as a 5G core network node. Even so, pushing mobile core functions to space can still be controversial. The current 5G network functions are mainly designed for the terrestrial uses. Can they really work well in space? In this talk, we study this problem from the state management perspective. Let's first look at how mobile networks work on Earth. The terrestrial mobile network defines many control plane functions to facilitate data plane forwarding. To use internet services, the device should first set up a session toward the fixed gateway. This session is stateful by design to facilitate traffic delivery, mobility management, QoS, billing, and security. As the device moves, it should retain the data access by migrating the session states to the new service area. Before these state operations are completed, the data service would be blocked. All these procedures implicitly assume that the base stations and core network nodes are fixed as service anchors. These infrastructure nodes are trusted, untampered, and reliable. Now, the question is, can these stateful operations work well in space? Unfortunately, our study shows a negative answer. Unlike fixed terrestrial infrastructure, LEO satellites move very fast in an unreliable, untrusted outer space on a global scale. This challenges basic assumptions of terrestrial mobile networks and threatens their scalability, performance, and resiliency. In our paper, we have analyzed different options of splitting mobile core network functions between satellites and terrestrial nodes. We found 3 key deficiencies. Number 1, each stateful session is coupled with an anchor gateway. If this gateway is placed in the terrestrial home network, it will become the centralized bottleneck, because all global users' control plane signaling and data plane traffic will be redirected to it. For example, it is known that one web's ground station must process 10,000 handovers every second. Our experiments also show 10 seconds of average signaling delays in operational satellites, which cannot meet 5G's stringent latency requirements. Then how about pushing this anchor gateway to LEO satellites? This seems to eliminate the centralized bottleneck. However, it causes even more serious scalability concerns. The terrestrial mobile network tracks a user location and service by its service areas. The service areas are coupled with the fixed anchor node's logical IDs. Such logical service areas will be unstable if the anchor nodes are moving. If pushing mobility functions to the fast-moving LEO satellites, the service areas will start to move, which will never happen in terrestrial networks. In this case, even if the users are static, they will be forced to switch service areas as satellites move. Then, their session states must be migrated between satellites. The issue is that each LEO satellite only has 160 seconds transient coverage for its thousands to tens of thousands of terrestrial users. As it moves fast, it will trigger simultaneous migrations between its users. Our experiments show that each LEO satellite will experience 10,000 to 100,000 signal messages every second, which will exhaust satellites' limited hardware and disrupt user services. Even worse, stateful core network functions in satellites are at higher risks of failures and attacks. Unlike terrestrial infrastructure, the moving satellites are exposed to the harsh, untrusted foreign locations. In reality, LEO satellites are prone to failures from radiation and solar activities. When the failure happens, the entire signaling procedures will be blocked. Moreover, when exposed to the foreign locations, satellites face many attacks by adversarial countries and nearby malicious satellites. Jamming satellite links can easily block the stateful procedures, and eavesdropping can also leak sensitive states like authentication vectors and permanent keys. For more details, please read our paper. Fundamentally, all these problems are rooted in the stateful mobile core network function design in 5G, which suffers from the extreme satellite mobility in the harsh outer space. So, how to solve these problems? The conceptual solution looks very simple. Let's decouple core functions from states to mitigate the performance bottleneck, signaling storms, failures, and attacks. But the challenge is that how to retain carrier-grade services after this decoupling. This results in 3 fundamental questions. 1. What session states are must-haves for the orbital core? 2. Where are these states placed if not in satellites? And 3rd, how can orbital core functions work with these states? Our solution, called SpaceCore, solves these problems with localized geospatial state management. It explores 3 core ideas. First, to mitigate state migrations between satellites, SpaceCore shifts from logical service areas to geospatial service areas. This stabilizes service areas and simplifies location states under satellite mobility. Then, to decouple states from satellites, SpaceCore delegates the states to the local devices. This local state repo can assist satellites in establishing local sessions without redirecting to the terrestrial home network. So here are the SpaceCore's high-level components. It has a terrestrial home network, LEO satellites, and devices. The terrestrial home is a legacy mobile core that runs all control plane functions. The satellites are networked with inter-satellite links. They run stateless gateways in a decentralized fashion, which eliminate centralized bottlenecks. Satellites directly fetch states from local devices during the session establishment or mobility. In the following, I'm going to show you the key ideas behind the SpaceCore. For more details, please read our papers. To mitigate state migrations between satellites, SpaceCore decouples the service areas from satellites. To achieve so, it redefines a service area as a geospatial cell rather than a logic area which is coupled to a specific moving satellite. This ensures each service area remains stable despite satellites' extreme mobility. Once decoupled from the geospatial cells, the LEO satellites no longer need to track the device location. This eliminates most logical location states, such as cell IDs and tracking area IDs. Instead, SpaceCore only keeps the device IP address as its location state. It embeds its geospatial service area ID into the IP address. In our paper, we have discussed how to divide these geospatial service areas to simplify the routing between satellites. For more details, please read our paper. For other states such as device ID, QoS, billing, and security, SpaceCore delegates them from satellites to local devices. Our key insight is that local devices naturally form a scalable, resistant, and secure state repository for the fast-moving satellites. Today, most of these states are readily available in devices once the device is registered to the terrestrial home network. Afterwards, they are almost always on unless the device is detached. They are free of exhaustive state migrations or leakage in satellite mobility. With the device as state repo, SpaceCore localizes session operations. When the old service satellite leaves, the device should re-establish its session to a new satellite. To do so, it piggybacks its state replica to the new satellite during the radio connectivity setup. If authorized to access these states, the new satellite can locally install them to immediately start services. By localizing session establishments, SpaceCore prevents sensitive state leakage. Upon satellite failures or attacks, the device can quickly migrate to other satellites and recover services with its local state replicas. Of course, offloading states to local devices is not without costs. Some devices can be compromised, selfish, or even malicious. They may manipulate the states for their own benefits. SpaceCore avoids this with home-controlled state updates. Note that the device-side states are assigned by the home during the initial registration. At this moment, the home can attach a digital signal of these states. If the device modifies the states, the satellite will detect it by checking the signature. Then it will roll back to the legacy 5G procedures. For more details, please read our paper. We prototype SpaceCore with Open5G-S on commodity hardware used by operational 5G satellites. We evaluate SpaceCore with operational satellite and 5G signal datasets which have been publicized. We compare SpaceCore with the legacy 5G and other solutions in terms of scalability, performance, and resiliency. Compared to existing solutions, SpaceCore reduces signaling cost by 1 to 2 orders of magnitudes. Its local state retrieval significantly saves state migrations between satellites and removes terrestrial home. Its geospatial mobility management avoids most state migrations between satellites. Compared to the legacy 5G, SpaceCore's local state management saves the signaling delay by up to an order of magnitude. This delay reduction also saves TCP stalling time for better application performance. SpaceCore is also resistant to attacks and failures due to its stateless nature. In summary, we show today's stateful core suffers from satellites' extreme mobility and exposure to unreliable outer space. This motivates us to make a case in 5G with SpaceCore, a device-assisted stateless core in space. Looking forward, we believe a native stateless architecture in 6G and beyond will be necessary to unleash the potential of LEO satellite megaconstellations. Thanks for your listening. I'm happy to answer your questions.
Hi, thank you for the presentation. So the 5G standards already propose network functions called as unstructured data storage function, which is also called as UDSF, for exactly this purpose, which is to offload the user state from the NF to the database so that the NF can be purely stateless. So you could actually implement it at per satellite, and during the handover, the satellites can easily hand over the state from one UDSF to next UDSF. Have you explored this option, or like did you see any problem with that? And because of this, you chose to go to the home network or offload the state to the user device?
Yes, that's a very good question. So we are aware of the 5G's state repos. So we also thought about the feasibility of using this option. The issue is that where should we place this state repo? So if we place the state repo to satellites, so we will face similar issues as satellites move around. We will still have this state migration between satellites, and we will suffer from signal storms. If we put the state repo to the terrestrial home network, then all these state migrations would still be redirected to the home network, which will cause a centralized bottleneck. So to this end, we think that we basically follow the similar logic to the UDSF, but it all depends on where we place the states. So you can think of the local devices in SpaceCore as a decentralized UDSF. We basically localize all states in the local areas without migrating states between satellites or between the satellite and terrestrial homes.
Hello, thank you for your talk. I may be misunderstanding your architecture, but it seemed from my perspective that a lot of the changes you're making are to the base stations, the G-Node B, rather than the core network. So I'm wondering, you talk about this home network that's terrestrial based. Is that largely a standard 5G core network, or is that also fairly custom compared to the base stations on the satellites?
It's largely a standard 5G core network and the base station. So in designing the SpaceCore, we are trying to be backward compatible with terrestrial 5G, and we hope we can seamlessly integrate the 5G satellites with terrestrial 5G. So we try to leverage the readily available state replicas in devices and in-band signaling to achieve this localized state management. So in that sense, we are not changing too much about the current 5G signaling messages, or we are not adding new states to the current 5G. So in my opinion, we are mostly backward compatible with terrestrial 5G network.
Hi, Wenji, Dave Oran. If I understand the architecture correctly, wouldn't the terrestrial network work a lot better if you did this? We would be a lot more resilient to disasters. You'd be able to soft state move states when various components of the terrestrial network fail, or links among the terrestrial components fail. I guess I wonder, why wouldn't you just do this for everything? I understand the backward compatibility and you have installed infrastructure and stuff like that, but isn't this overall just a better architecture for how to build a mobile network?
Well, so I agree with you. The terrestrial home network is the only component that is still vulnerable to the disasters. But the key is that we are talking about a global satellite network everywhere. So in that sense, if you compare the satellite network we talk about here versus a pure terrestrial network, if you think about a pure terrestrial network, we deploy base stations and core network everywhere. If in one area we have some earthquakes or disasters, the infrastructure is down, then in this area we cannot have any services. But in case we still have satellites and the home network is still alive, which can be far away, right? For example, we have these terrestrial home network in the US, but we have some disasters in Africa. But in that case, then we can still use satellites to offer these network services to these rural areas. So in that sense, SpaceCore is more resistant to a pure terrestrial network in most areas except the home network. The home network is still the only vulnerable places, but I think that is hard to avoid because anyhow, mobile operator needs a place to take full control of this network infrastructure.
Okay, thank you. And with that, so thanks, Yuanji, and with that, the session comes to an end. And